I'm happy to introduce our next speaker, Piotr Borodulin-Nadzieja from University of Wrocław, measure avoiding and measure supporting filters.
Thank you. Thanks for the invitation. And I wasn't aware that this conference is so big until yesterday. Congratulations to the organizers. I will speak today about two things, two projects. They are not finished, maybe even far from being finished. And it is with Jonathan Cancino, Adam Morawski, and the second project is with Artyom Rączyński. Okay, so I'm interested in the structure of P omega mod finite, one of the most beautiful structures of set theory. And I want to look at it from the topological point of view as a stone space. So just quick reminder, what is stone space? So stone space is the space of ultrafilters on omega, and the topology is induced by a subset of omega. So if you have subset A, the basic set induced by this set is the set of all ultrafilters which possess this A as an element. And omega star is just this stone space of P omega mod finite. So we exclude principal ultrafilters. There is a theorem that this omega star is not homogeneous. So what does it mean that the topological space is homogeneous? It means that whenever you have 2 points, x and y, there is an auto-homomorphism which sends x to y. So it says that if something is homogeneous, it means that there is only a topological type of points in this space. So this is not surprising that omega star is not homogeneous, because omega star is very complicated. It's extremely complicated structure, so it should contain different creatures. So this theorem by Frolik is no surprise, but the proof of this theorem by Frolik has a disadvantage. The disadvantage is that Van Douwen didn't like it, and he claimed that the proof is not decent. The proof was the cardinality argument. So Frolik just used cardinality argument to show that there has to be many topological types. So what does it mean, a decent proof of non-homogeneity? It means that we indicate that we show 2 particular topological types which are not the same. I mean, 2 different topological types in omega star. And there was a very natural candidate of such type, which is different than some other types. And here comes the famous the p-point property, I mean the definition of p-point. So an ultrafilter is a p-point if whenever you have countable family of its elements, you can find a pseudo-intersection of this family in the filter. So pseudo-intersection means I'm pseudo-intersection if I'm almost contained modulo finite sets in every element of the family. And actually, this definition can be, we can define p-points in the general topological setting. Something is a p-point if whenever you have countable family of open sets, you can find neighborhoods of this point. You can find an open neighborhood which is contained in each element of this family. So under CH, under continuum hypothesis, there are p-points in omega star, and the proof is easy. And there are points which are not p-points. So if you extend a filter of density 1 sets, if you don't remember the definition, it's not so important now. Just every ultrafilter has to contain sets of arbitrary small density. So if an ultrafilter is a p-point, then it has to contain a set of density 0. So it cannot extend density filter. So under CH, we have this decent proof of non-homogeneity, right? But unfortunately, it doesn't work in ZFC because Sherlock proved that there are no p-points in omega star. So people had to think about other candidates for topological types. And one of these candidates is something called weak p-point. Weak p-point is a point which is not cannot be reached by any countable set as a closure, as a point in a closure. And each p-point is a weak p-point, of course, by linguistic reasons. But mathematically, it's also quite clear, right? That if you have countable set, you can avoid more and more points by open sets, and then you have inside the open set which separates you from the countable set. And finally, Kunen showed that there are COK points. I'm not going to define it. It's quite technical notion. And what is only important is that these COK points are weak p points, and they do exist in ZFC. Excuse me, where? K is a topological space. Just this definition works for arbitrary topological space. But of course, we are interested in the incarnation in omega star only. Yeah, so the Kunen's proof. So this finally is a decent proof on non-homogeneity of omega star, because of course there are guys which are not weak p points. Just take discrete countable sets and close it, and then you have something in the remainder which is not a weak p point. But the proof is quite involved. Even this definition of COK point is involved, and then the proof is even worse. Okay, so I will be speaking about measures on omega. So for me, measure is a finitely additive function which assigns 0 to empty set and 1 to omega. And we'll be interested mostly in measures which are vanishes on points. Okay, this is maybe not so important, this proposition. Just if you are irritated by an idea that a measure can be not sigma additive, this is to calm you down that if you have finitely additive measure, then it can be extended uniquely to a sigma additive measure on the Stone space. Okay, and examples of measures. So ultrafilters are measures, not formally, but if you have ultrafilter, you can take a function which assigns 1 to elements of ultrafilter and 0 to the rest, and this is a measure. And something more non-atomic, if you have an ultrafilter on omega, then you can take the following function. So you take a limit along ultrafilter of this ratio. So if you take the normal limit, this is exactly definition of asymptotic density. But if you take normal limit, it may or may not exist. Yeah? But if you take limit along ultrafilter, it always exists by compactness, and it is always a measure, and this is measure extending asymptotic density. And in yes.
But does it mean that it's already sigma additive for those unions for which it's no? What is it?
I mean, no. Look, for example, if you are interested in measures which vanishes on points, then if you want to have sigma additivity, then omega is also measure 0. Yeah, so these measures on omega are very far from being so sigma additive, usually. Look, if you take the Stone space, then the subset of omega becomes a Klopen subset of the space. and you have this, so you can leave this measure, and then you can extend it in this sense. Sorry, it's quite laconic, this proposition, but as I said, it's not so important maybe for today's talk. Okay, so now that was introduction, and now I want to speak about results. Let me start from this definition. I think it's new. I don't know. Maybe it was known but I haven't found anything in the literature. So we say that a point in a topological space avoids measures if whenever we have a measure which is not concentrated on this point is not in the support of this measure. And the support is the intersection of all closed measure one sets, the support of the measure. So think, for example, about unit interval. So no point in the unit interval can avoid measures because it cannot avoid Lebesgue measure, right? Lebesgue measure is non-atomic, so it's 0 on every singleton. And if a point avoids measure, it exactly means that there is an open neighborhood of this point, which is of measure 0. So P points avoid measures. Because if you have a point and a measure which is 0 on this point, it means that you can find neighborhoods of arbitrary small measure. Say you can find un of measure 1 over n, but then by p pointnets you can find an open set, open neighborhood of the point of measure 0, and that's it. And also this mysterious C-OK points avoid measures, but it's more complicated. And of course you can define some atomic measures. I mean, of course or not of course. If the topological space is not scattered, then you can always define a non-atomic measure on it. So there are points which do not avoid measures, even non-atomic ones. Okay, so let me. Okay. So the natural question is, if you look at this definition, it resembles a little bit the definition of weak P point. And the natural question is, what is the relation between weak P points and these guys? And in fact, weak P points can be defined in the terms of measures. So weak P points are exactly points which avoid strictly atomic measures. Strictly atomic measure is a measure concentrated on a countable set. And the problem is, what is the relation between weak P points and points which avoid non-atomic measures? So the picture is like that. Can you hold it? Thank you. We have C-OK points, measure avoiding guys, and then we have guys which avoid strictly atomic measures, and these are exactly weak P points. And we have ultrafilters avoiding non-atomic measures. And the question is, what is the relation between these two? And they are quite independent. So you can find always a weak P point which do not avoid non-atomic measures, but under CH you can find something which is not weak P point which avoids non-atomic measures. So what is the motivation for this? You know. So, okay, there is a nice proof by Kuhnen of non-homogeneity of omega star, but it's quite complicated. So I thought that, okay, maybe you should look at this problem of non-homogeneity from the measure theoretic perspective. And maybe using this concept of avoiding non-atomic measures, you can find some simple proof of non-atomicity, because all you have to do is just to find a point which avoids measure in the non-atomic measures in the omega star. But I think we are far from that. If actually it is not even not easy to find such a point under CH. Of course, it's very easy if you use p points, but we have to. We don't want to use p points for that, right? We want to have something new. So even if you want to perform some construction under CH, the naive approach would be to kill all the measures, but there are too many measures, so it is impossible. So apart of killing measures, you can kill trees. So picture by tree now I mean family of subset. I don't know if you can see it, of omega, which looks like that. So you divide into 2 and then into 2 and so on. So the shape of this tree is like that. It's just dyadic tree, but it consists of subsets of omega. And maybe don't read this definition. The point is that, look, I can say that if I have branch in this tree, I will say that a set touches it if every element from this branch has infinite intersection with the set. So we can define p-point using this terminology and say that p-points are exactly guys who, for every tree like that, has element which touches only one branch. And this definition says more or less that this is some generalization, that ultrafilter has a set which perhaps touches more branches, but the set of branches it touches is of Lebesgue measure 0. Because I mean, when I speak about branches, I speak about Cantor set, right? So yeah, if we can avoid trees in this sense, we can avoid non-atomic measures, and under CH we have proved that it is possible, but of course it's very unsatisfactory. But I still hope that maybe there is some way to construct such a point avoiding non-atomic measures, but maybe this is dead end. I don't know. Okay, so now the second part, and now this part also concerns some kind of generalization of the property of p-point, and also with the help of measures, but in completely other direction. So say that a measure is a p measure if whenever you have a descending sequence, you can find a pseudo intersection such that the measure of the pseudo intersection is a limit of the measures from this family, from this sequence. So again, you cannot have interesting measure which is sigma additive on omega. So you cannot have a measure which is continuous from above on omega. But you can have measure which is almost continuous from above. This is that, right? And each point is a p measure, right? Because then you have to check, you have a family of sets. So if at least one of them is of measure 0, so outside of the ultrafilter, then take empty set from the pseudo intersection. And if all of them are of measure 1, then just use the p-pointness and you obtain the proper pseudo intersection. And also, this is a little bit more complicated. If ultrafilter is a p-point, then this measure, this extension of asymptotic density along this ultrafilter is also a p measure, non-atomic one. Okay, and consistently, there are no p measures. It was proved by Meckler. And the big problem in this area is it consistent to have a p measure but no p-point? So a candidate for this model is a silver model. So quite recently, Gdansk and Guzman proved that in the silver model there are no p-points. It was quite surprising because the silver model is one of these canonical forcing models, and yeah, it was. I think people didn't suspect that there are no p-points. Because p-points are in most of the models you can think of, right? There are a lot of axioms which implies that there is a p-point. So the p-points models without p-points are very rare. Also, Gdansk and Guzman proved that it is not known that there is a p-point in the random model. Maybe it sounds strange, but actually it was achievement, because before it was known that there is a p-point in the random model. But they found a gap in a proof. But anyway, there are strong indications that there is a p-point in the random model. So if you add omega-1 Cohen reals first and then force by random forcing, there is a p-point. Alan proved that square omega-1 in the Grant model implies there is p-point in the random extension. And also with Damian Sobota, we proved that there are p-measures in the random extension. And actually, every p-point from the Grant model can be extended to a p-measure in the random extension. By this, I mean that if you take this p-point in the Grant model, you can find a p-measure in the extension such that it is one on every element of this old p-point. Okay, so the natural question is there is a p-measure in the silver model? And that was this is the subject of the second project I'm talking about. And okay, just a remark, by omega-omega boundedness of silver forcing, if such a measure exists, it necessarily extends p-measure from the Grant model. And first of all, Adam Morawski proved that no rapid filter from the Grant model can be extended to a p-measure in the silver extension. And I'm not going to define what is rapid filter, but you can have, the important thing is that you can have a rapid p-points under CH. So it is not like in the case of random model, right? In the case of random model, every p-point from the Grant model could be extended to a p-measure, but this is not the case of the silver model. And then we managed to make a few steps forward. So I will say that one measure is, so mu is Rudin-Blas below nu. If we can have a partition into finite sets of omega, such that if you glue these elements of these chunks of this partition into points, and consider a measure on this points, and if it is measured mu, then if you lift it up, it's measured nu. So so this is a concept from, I mean, this is one of the most important ordering on ultrafilters, but here we use it for measures. It also makes sense. And what we have that if you have a measure in the Grant model and you can find an ultrafilter Rudin-Blas below it, then it cannot be extended to a p-measure in the silver extension. This is the same theorem. So what it means? It means that, for example, that no p-point from the Grant model can be extended to a p-measure, right? Because if you have measure which is already an ultrafilter, then. But moreover, if you have a measure which is defined as an extension of asymptotic density along an ultrafilter, then you have a p-point Rudin-Blas below it. So the situation is like that all the measures, for all the examples which are known of p-measures in the under CH, we are able to show that they cannot be extended to a p-measure. But of course, maybe we don't know about something. Yeah, maybe there is some strange p measure which lives in CH and which cannot be extended. We don't know. For sure, I know that in the random model there are p measures which do not have any ultrafilter Julien-Blas below. But I don't know about CH. And maybe I will just put it in some broader contexts at the end. So there are different kinds of complexity of filters. So for example, you can define a filter to be CCC if the structure of, I mean, perhaps I should rather write the dual ideal, not the filter, but I hope you understand it. But the structure of P omega mod this filter is CCC. I will say that filter supports a measure if it is a filter of measure one sets for some measure. And finally, a filter is non-meager if it is non-meager as a subset of the Cantor set. So what we have the ultrafilters are the most complicated guys. Every ultrafilter supports a measure, an ultrafilter, right? If a filter supports a measure, then it has to be CCC. And if it is CCC, it is non-meager. And then the huge problem here is, I think it is still open. If there is it consistent that there are no non-meager p filters, right? So we know that there are consistently no p points. We know that consistently there are no filters supporting measure. It is also known that consistently there are no CCC filters. This is a result by Szelach, Frankiewicz, and I think Wysbierski. And what we are doing with these p measures can be seen as a part of this situation. Okay, so that's all. Thank you for the attention.
Questions? Okay, if not, then let's thank Piotr again. And we continue with the next talk.